Aside from the nuclear hazards involved, all implosion-type atomic weapons are hazardous because of the high explosive materials they contain. When these weapons are accidentally exposed to fires, such as those resulting from aircraft crashes, firefighting and aircraft rescue personnel need to have a realistic understanding of the extent of the dangers involved. To obtain factual information for meeting such emergency situations, the Naval Ordnance Test Station recently carried out an investigation of the effect of fire on 3 naval weapons as part of the Navy's Atomic Weapons Vulnerability Program for 1958. The 3 atomic weapons tested were Bohr, a 30-1/2-inch aircraft rocket, and 2 depth bombs, alias Betty and Lulu. The weapons were suspended from a double-arch A-frame over a fuel pan that was filled with aviation gasoline for each test. Preliminary fire tests had established the temperatures produced by aviation gasoline to be about the same as those produced by JP-4. Each weapon was suspended in the zone of maximum temperature above the burning gasoline. All tests were conducted under similar conditions for purposes of comparison. Blast pressures produced by warhead detonations were recorded by 18 indenter gauges located at various distances along 3 radial lines emanating from the center of the test site. Each gauge was installed so that its pressure plate was level and flush with the surface of the ground. Fragment collector pads, constructed of Celotex, were installed in a semicircle 75 feet from the test weapon. The face of each pad was covered with aluminum foil to retard ignition from radiant heat and flaming gasoline. Radioactive contamination air samplers and fallout collector plate stands were installed on 32 radial lines out to 6,000 feet. Thermocouples for recording temperatures were embedded in the high explosive material, as well as on structural and electrical components contained in the weapons tested. The first test was conducted on a Bohr weapon that contained a live motor and a dummy warhead. A Bohr weapon contains, in addition to an atomic warhead, a solid propellant rocket motor. This fact compounds the hazards when this weapon is exposed to fire. This Bohr weapon was burned to destruction to determine how long the rocket motor would survive after the gasoline was ignited. 1 minute and 37 seconds after ignition of the gasoline, the motor ignited momentarily. This chuffing occurred 3 different times during the next 7 seconds. Sustained burning began at 1 minute 44 seconds. The rocket exhaust, deflected by a thrust neutralizer, threw burning gasoline in all directions, creating that large fireball. No explosion occurred. The motor burned for approximately 3 seconds. Here is that same test, photographed from a nearby hill. This view shows the extent of the area covered by burning gasoline when the motor burned. It is readily apparent that the combination of live rocket motor and a live warhead in one weapon presents a greater hazard than either one taken separately. Disregarding nuclear contamination, atomic weapons are no more hazardous than conventional high-explosive weapons of comparable size. An important part of the design of every atomic weapon is a means of preventing any nuclear reaction in case of accidental detonation. A nuclear-safe Mark VII warhead was tested in a Bohr weapon containing a dummy motor. In this test, the weapon was burned to destruction to determine the elapsed time from ignition of the gasoline to burning or detonation of the warhead's high explosives. The weapon's fissionable material was replaced with tuballoy to measure the amount of radioactive contamination to be expected from a fire accident involving a war reserve weapon. The bright flash was caused by the detonation of the trapdoor charge while the charge was still inside the IFI housing. The fact that the warhead proper did not detonate at the same time indicates that even at elevated temperatures, the high explosive material in the Mark 7 warhead is relatively insensitive to shock and impact. Burning of the high explosive material began as early as 1 minute 20 seconds. Burning became general at 1 minute 45 seconds. No explosion occurred. However, pieces of high explosive material were thrown around the immediate vicinity of the test site. The tubuloid capsule recovered from the fuel pan was slightly charred and oxidized on the surface, but otherwise was undamaged. No measurable radioactive contamination was found outside the fuel pan. These fire tests had a twofold purpose. One, to determine the nature of each weapon's response to fire, and two, to evaluate the effectiveness of a shipboard firefighting technique in preventing detonation of the high explosives in atomic weapons involved in fire. A 2.5-inch Navy all-purpose nozzle was located on each side of the next bore weapon tested. Each nozzle, supplied with water at 100 pounds per square inch, was positioned to impinge cooling water directly onto the warhead section of the weapon, thus simulating a shipboard firefighting technique. Since the first bore warhead had ignited at 1 minute 25 seconds, this weapon was allowed to burn freely for 50 seconds before the application of cooling water was begun. This was done in an effort to establish a safe delay time, after which the cooling water would still be effective in preventing ignition. The high-velocity water spray deflected the flames so that they no longer engulfed the weapon, even though the fire continued to burn. The high explosive material did not ignite. Total duration of the fire was 20 minutes. Cooling water was applied for 36 minutes. Neither burning nor detonation of the high explosive materials occurred. This same weapon was again subjected to fire, and since damage to the ballistic case exposed the high explosive warhead directly to the flames, a free burning time of 50 seconds was again chosen. It was reasoned that cooling water applied to this damaged weapon at 50 seconds would roughly approximate a free burning time of 90 seconds for an intact weapon. The high-velocity water spray again deflected the flames from the weapon. The fire burned for approximately 20 minutes, and cooling water was applied continuously from 50 seconds to 36 minutes. The weapon's high explosive material did not ignite. It is possible, however, that the evaporation of entrapped water from the first burn test may have contributed a significant amount of cooling during the free burning period of this second burn test. The insulation on all the exposed wires was burned away, and practically all of the aluminum skin over the entire weapon was destroyed. The latching cover on the IFI was warped but still in place, while both of the battery boxes had broken open. Once again, this weapon was subjected to fire. However, this time no cooling water was applied. 2 minutes and 10 seconds from ignition of the gasoline, the trapdoor charge detonated. 15 seconds later, the remainder of the warhead detonated low order, scattering high explosive material and other debris over a large area. One piece of high explosive material weighing 10 pounds was recovered 300 feet distant, and several smaller pieces were found even farther away. This is that same test photographed from another position. The force of the trapdoor charge detonation drove the tubuloid capsule back into the warhead cavity. The capsule, minus the stub cone, was found intact after the test. Blast pressures ranged from a high of 40 pounds per square inch at a distance of 10 feet to a low of 2 pounds per square inch at 100 feet. This weapon, already extensively damaged, was then burned to destruction. After the high explosive had begun to burn, cooling water was applied for approximately 4 minutes to see what effect it would have on the burning HE. The burning rate was reduced while the cooling water was applied. After the water was shut off, the high explosive material burned very brilliantly for about 6 minutes. Roughly 10% of the tubuloid capsule, later found in the fuel pan, had been burned away. Analysis showed that the gases from the fire carried slight tubuloid contamination out to a distance of 1 mile. To summarize the results of the Boer fire tests, of the 3 Boer weapons tested, 2 warheads burned with no detonation. 1 detonated low order. Cooling water was effective in preventing ignition of a Boer warhead when applied 75 seconds after starting the gasoline fire. Without the application of water, the high explosive material in a Boer warhead began burn in 1 minute 20 seconds. When subjected to the fires, the weapon was nuclear safe. That is to say, the tubuloid capsule was in the retracted position in the IFI housing. No attempt was made to cool the weapon in this first test. At 9 minutes 28 seconds, the high explosive ignited. 20 seconds later, it detonated. The detonation completely demolished the Betty weapon, the test stand, and the gasoline pan. Blast pressures recorded at ground level 10 feet from the center of the weapon were over 400 pounds per square inch. The tubuloid capsule was found intact about 60 feet from the center of the test area. A second Betty weapon was subjected to fire. This time, however, cooling water from the 2.5 inch water nozzles was applied 7 minutes after ignition of the gasoline. The weapon again detonated, this time at 14 minutes 53 seconds. This is that same test as photographed from another position. The detonation again completely demolished the weapon, the test stand, and the gasoline pan. This was the only vulnerability test involving a Mark 7 warhead in which the tubuloid capsule was broken up. The level of contamination adjacent to the fuel pan was approximately 2 grams of uranium oxide per square meter. The 4 blast pressure gauges, located within 10 feet of the weapon, were severely damaged by high-velocity fragments. The surviving gauges recorded pressures of 200 pounds per square inch, 16 feet from the weapon. The third and last Betty weapon tested was burned 3 different times. This is after the first burn, in which the weapon burned freely for 5 minutes before water was applied. The gasoline continued to burn for an additional 15 minutes. Damage was limited to destruction of the lightweight aluminum tail cone and to scorching and charring of the exposed portions of the hydrostatic switches and timers mounted on the aft bulkhead. This is that same weapon after the second fire. Water was applied after 6 minutes of free burn. The weapon survived without visual evidence of damage to the high explosive material in the warhead, even though a large hole was burned in the aft aluminum bulkhead. This weapon was burned for a third and last time, and no water was applied. A 5-knot wind prevailed during most of the test. Visible burning of the high explosive material was observed at 11 minutes. At 12 minutes 11 seconds, the warhead detonated low order. Unburned HE material was scattered to the rear of the test stand and the weapon's pressure hull was propelled forward approximately 100 feet. The tubuloid capsule was recovered intact near the place where the pressure hull came to rest. No measurable air contamination was present. Of the 3 Alias Betty weapons tested, 2 detonated high order and 1 detonated low order. Cooling water, when applied as late as 6 minutes after a weapon was engulfed in flames, was effective in preventing detonation. Without the application of cooling water, an Alias Betty weapon will probably detonate. The last atomic weapon to be subjected to the fire tests was Lulu, a depth bomb employing the Mark 34 warhead. This test is typical of 6 different fire tests involving 6 different Lulu weapons. No detonation occurred in any of the Lulu tests. Damage was confined to melting of the tail section and to ejection of the nose cap and the forward half of the warhead case caused by pressure buildup inside the warhead compartment. Water was effective in preventing destruction of the weapon when applied as late as 8 minutes 30 seconds. And was not effective when applied at 10 minutes. These fire tests, conducted on 3 different naval atomic weapons, were limited in number. For this reason, the information obtained cannot be considered conclusive. Bearing this in mind while examining the test data on these charts, an analysis of the results obtained indicates that the Mark 7 in a bore weapon, when involved in a fire accident, will burn and occasionally will detonate low order. Note on this chart that the high explosive material in the Bore 1 weapon, containing a live warhead and a dummy motor, ignited at 1 minute 20 seconds. No water was applied and no detonation occurred. With Bore 3, cooling water was effective in preventing ignition when applied at 75 seconds. An entirely different result was obtained when the Mark 7 warhead was tested in the depth bomb Alias Betty. In this case, the confining effect of the steel pressure hull caused the warhead to detonate. When cooling water was applied to Betty 2 at 7 minutes, sufficient heat had already been transferred into the weapon to cause the warhead to detonate at approximately 15 minutes. In spite of the fact that cooling water had sprayed onto the weapon continuously for 8 minutes. Betty 3 was saved when cooling water was applied at 6 minutes. The depth bomb Lulu appears to be the least hazardous of the 3 weapons tested. None of these weapons detonated. When cooling water was applied to Lulu 4 at 7 minutes 35 seconds, the weapon was saved. Lulu 6 was saved when cooling water was applied at 8 minutes 30 seconds. Application of cooling water to Lulu 5 at 10 minutes was too late. The high explosive ignited and burned. Results of these naval atomic weapons vulnerability tests indicate that the metallic radioactive materials in either the Mark 7 or Mark 34 warhead do not present an undue hazard to firefighting personnel. Standard radiological monitoring and decontamination procedures are adequate to cope with this problem. However, the Mark 34 and other gas-boosted warheads contain a radioactive gas that is extremely toxic. For this reason, firefighting and rescue personnel should avoid breathing any fumes emanating directly from the burning weapon. The 3 points to remember when an atomic weapon is involved in a fire accident are: 1. The possibility of a nuclear reaction is extremely remote. 2. Standard clothing worn by firefighting personnel is adequate protection from radioactive contamination. And finally, detonation of the high explosives can be prevented by timely application of cooling water.